Hi students, welcome to Inside Physics. I am Srinivas. Today we are going to discuss the topic of moment of inertia, which is an interesting concept in rotatory motion. See, moment of inertia. In this topic, we previously learned about what is inertia of a body. See, inertia we know it is the inability of a body to change its state of rest, or if it is moving in a uniform motion, its state of uniform motion by itself. So that means a body which is at rest or in uniform motion, it cannot change its state. That means it cannot come out of the state of rest by itself, or whether it is in a motion moving with uniform speed, and it continues to be in the same speed, and it cannot change its state of uniform motion by itself. By itself means it requires an external agent, something like an applied force, to change its state of rest or motion. That is called inertia. By itself, the definition says it is a measure of mass. Inertia is a measure of mass. That means if the mass is more, inertia is more. So a heavy object is having high inertia. That means inert, means unable to change or react. So a body cannot change its state of rest or uniform motion by itself. Rest or uniform motion by itself is called inertia. So there are three types of inertia: inertia of direction, inertia of rest, inertia of motion. So here, if it is a linear motion, we call it as inertia. That means linear motion is a straight line motion. And if it is a rotatory motion or circular motion, here the same inertia is called moment of inertia, that is rotational inertia. See, rotational inertia is quite analogous to the inertia in linear motion. So, how to get the moment of inertia for some different bodies, so which are rotating? The concept of rotational inertia will arise only in circular motion, and we can say that any object like a regular shaped or an irregular shaped object can be in rotatory motion, and we can find the moment of inertia of that particular object with some concept here. See, if I take an object, some regular shaped object like a square or a sphere. So for now, I'll take a square, and we know the center of mass will be exactly at the center of the sphere, because this is a regular shaped object and it is having a symmetry over all its sides. So if it is rotating about an axis passing through the center of mass, okay, then we can say this is having some moment of inertia. Generally, it is represented by I is equal to mr square, where m is the total mass of the object and r is the distance of center of mass from the axis of rotation. So here, how to get the concept of moment of inertia involving the kinetic energy of each particle when an object is rotating. Suppose consider a rigid body which is of irregular shape. Okay, so we have so many particles in this rigid body, and if you consider this as axis of rotation, so each particle m1 of, and the second particle of mass m2, and the third particle is of mass m3. There may be n number of particles. For consideration, we will consider 3 or 4. and this is the axis of rotation. What is the axis of rotation means? This entire object is revolving on this axis like this. Okay, so this is called axis of rotation, and we can take the rigid body, and it is of irregular shape, and there are so many particles inside. So if any particle is moving, either it is a linear motion or rotational motion, see, it is having a linear velocity. It is a linear motion, we can say it is moving with some linear velocity, and it is also having some rotational motion. We can say the linear velocity of a particle which is in rotatory motion is equal to r omega. Okay, this is the radius. R is the distance of the particle from axis of rotation. Omega is nothing but angular velocity. We know every rotating particle or object is associated with some angular velocity. What is angular velocity? It is nothing but displacement by time, and if you consider the instantaneous angular velocity, it is rate of change of angular displacement. So we know the details of angular velocity, and we have already seen in the concepts of rotational motion. Now here, what is the kinetic energy of each particle? That means we can say the kinetic energy of each particle is nothing but half mv square. So here we can replace v with r omega because it is in rotational motion, and we know the relation between the linear velocity and angular velocity is equal to v is equal to r omega. So if you replace v with r omega, it becomes half m r omega whole square. This will be omega square. So this is kinetic energy of a particle inside the rigid body when it is doing the rotatory motion with some angular velocity omega. So here if you observe this one, I can write this as omega square half m r square. We know in rotatory motion of a body, each particle, whether it is closer to axis of rotation or farther away from the axis of rotation, the angular velocity of each particle is same as per the rules of rotationary motion. That's why omega angular velocity I have kept aside, and this is, see, called the moment of inertia of an individual single particle with mass. Suppose this is m1, I say a particle mass m1, and this r1 is the distance of particle m1 from the axis of rotation. So here this is the moment of inertia, and this I can write it as if it is I omega square. Okay, this is rotational kinetic energy of a particle which is in rotatory motion around the axis of rotation. So I omega square, and we can put 1 by 2 before this, half I omega square. If you observe both these formulas, kinetic energy in linear motion and rotational kinetic energy for a particle or object in rotatory motion, you can observe the similarities. The mass is replaced by the moment of inertia. So the mass is a measure of inertia in the linear motion, and I here is a measure of rotational inertia in rotatory motion. Omega is angular velocity, here v is linear velocity. So this is the similarity of measuring kinetic energy in linear motion and kinetic energy in rotatory motion. Now if I say this is moment of inertia of a single particle, how to get the moment of inertia of the whole body, whole rigid body? That means if I can say there are n particles inside the rigid body, I can add the moment of inertia of each particle like this. Okay, if there are n number of particles, so this as a summation we can write I is equal to 1 to n m I r I square as a summation of individual moment of inertia of each particles of a rigid body which are at a distances r1, r2 and r3, and there may be n number of particles. We can add all the sum of moment of individual inertias and we can have a summation which gives the total moment of inertia of the entire body. So this, suppose the whole mass of the body is m and we can say the moment of inertia is r, where r is the center of mass of the object. See, here what we have done is how we got the formula for moment of inertia, which is product of mass into distance of the center of mass of the object. Now, if the mass is increased, the rotational inertia, that means, see, moment of inertia is a measure of rotational inertia. So, and that if the distance is increasing, then the moment of inertia is also increases. So, if it is a continuous homogeneous body, it is not regular, it is having a continuous mass, and it is, if it is a homogeneous body, then we can write this as summation, and this summation is replaced by integration. So we'll see how to get the total moment of inertia in case of a continuous homogeneous body. So this moment of inertia and the summation is replaced by integration, because we, if it is a continuous body, we need to integrate with respect to the mass, where the mass will be changing with the distance, and at the same time volume is also changing. So here see, this r square we can write, and small mass where it is having a very low value when it is taken at some particular point. So this we can write the integration over the entire volume r square rho dV. We know mass is equal to density into volume. So for a small mass where we have taken in the entire body, and this is replaced by the density of the material into volume of that particular object where we consider, and this is integrated over the entire volume. So with this calculus method, we can get the moment of inertia in case of a homogeneous continuous body where the shape is quite irregular and the mass distribution is also irregular. Okay, this is how we measure the moment of inertia in case of regular and irregular shaped objects. So what is the physical significance of moment of inertia? In general, if you observe, see, a body which is very heavy is very reluctant to rotate, and we need some extra force to rotate it. And if it is also in rotation, we need some force, extra force to stop the rotational motion because of high moment of inertia, because of its high mass. Okay, so to get a better clarification, we'll see some examples based on this formula we got. I is equal to mr square. So If we take two spheres of one is of iron and one is of wood with same radius. Okay, so I've taken two spheres, one is of iron material and one is of wood material with both having same radius. Here, which one of these two spheres must be having the high amount of inertia? Means the iron sphere will have more amount of inertia. Why? Because see, the mass distribution, suppose we consider the axis of rotation for these two spheres is along the diameter of the sphere, then the mass distribution along the axis of rotation, this is the axis of rotation for both, radius is same, axis of rotation is same, the mass distribution along the axis of rotation is more for iron sphere. What is this? Mass distribution along the axis of rotation is more for iron sphere, and the same is less for the wood sphere. So the moment of inertia is more for iron sphere. See, the mass distribution means we only consider the mass along the axis of rotation, and its distribution means how it is distributed, the distance with the axis of rotation. So obviously the mass distributed with the particles is much more heavier, as we know the density of iron is more than density of wood. So this is how we can understand what is moment of inertia, and this plays a good role, significant role, while understanding the rotating objects. Okay, now we will take one more example for better understanding. See, if I take a disk, if I take a spherical disk and I'll take a sphere as a second object. Okay. Now, if I take the axis of rotation of this spherical disk and see, and the diameter here of the sphere is the axis of rotation. This axis of rotation is normal to the plane of the sphere, sorry, disk, and here the diameter is, the axis of rotation is along the diameter of the sphere. Now in which case of these two will have more moment of inertia? Here also, see, this spherical disk will have the moment of inertia more than this sphere, because as I said, the mass distribution along the axis of rotation here is more. The total mass is distributed along the axis of rotation, and here the mass is distributed, I already this is both having the same mass, consider both having the same masses. Okay, but even though they have the same masses, but the distribution of mass along the axis of rotation is more in case of this disk. That is why moment of inertia is more in case of a spherical disk. So these examples make us very easy to understand the moment of inertia. So here we will see what is a radius of gyration. Sometimes it is also called radius of gyration. It is represented by K. Radius of gyration represented by K. So what is radius of gyration? Okay, see, here if I take a rigid body with some irregular shape, the same example which I have taken for moment of inertia, and this is the axis of rotation. Okay, because this is a rigid body with irregular shape, the mass is distributed all along the shape of the object, and it is not regular. That is why we cannot have a center of mass exactly located at its geometrical center. Obviously, it doesn't have any geometrical center because it is having an irregular shape. Anyway, we can calculate the center of mass with all the theory we have. And suppose I find the center of mass here for this object. So the radius of gyration is defined as the distance of the center of mass from the axis of rotation of this object. That is called radius of gyration. Okay. Now here, see, if the entire moment of inertia we take in the previous theory, we have seen that moment of inertia is nothing but the summation of all individual moment of inertias of each particle, right? Then if the each particle is having individual moment of inertia and we can add it up, we will get the moment of inertia of total object. Here this k, the radius of gyration, gives the distance of center of mass from the axis of rotation, and we can easily say this is equivalent to, this whole summation is equivalent to mk square. See, where m is the whole mass of the object, what is m here? Summation of all individual masses m1. Here m is equal to m1 plus m2 plus m3. So summation of all individual masses. So here, instead of taking the each particle and its distance from the axis of rotation, we have taken the center of mass, because center of mass is nothing but where all the, it is a point where all the mass of the object is supposed to be concentrated, and we can take its linear motion as the motion of center of mass. So here it is rotating, and we cannot exactly get the distance of each particle, and we cannot see in this is a difficult process by having each particle's distance from the axis of rotation. So for the convenience of getting the moment of inertia, we will take the center of mass as a whole point of mass distribution, and we can get this done by this formula, and we can now equate as per equation this and this. We can say that mk square is equal to summation of I is equal to 1 to n mi or I square. Okay, here, see, this is what total moment of inertia. Now I can write mk square is equal to I, and that implies k square is equal to I by m. So that means k is equal to root of I by m. And the units for radius of gyration is nothing but it is a distance, so it can be measured in meters. So the moment of inertia is measured in kg meter square, as it is a product of mass and the square of the distance. So this is the unit for moment of inertia, and the unit for radius of gyration is meters. Okay. See here, the moment of inertia is not a vector, and even it is not a scalar, because it doesn't have a fixed value throughout the object. See, the moment of inertia is changing in different directions in the same body. So it does not have a particular direction, and it is not also considered as a scalar. So what kind of a quantity is moment of inertia? Means it is a tensor quantity. So moment of inertia is not a vector and not a scalar, but it is a tensor quantity. So what kind of quantity is a tensor quantity? So it is quite changing with the distance and distribution of mass. So they have two variables which can affect the a quantity, then it is called a tensor quantity. So this is about the radius of gyration and the moment of inertia, which can say the easy movement in the rotational motion and how it is affected by the mass and mass distribution, and the shape of the object also is having an effect on the moment of inertia. So this is the concept of moment of inertia and radius of gyration. In the next class we will see how to calculate the moment of inertia of different objects. Okay, something like a sphere, a circular ring, so a rod with some length L. Okay, so that's for all now. Thank you.